take you through some more puzzles from the logical journey of Zoombinis. I just want to say I'm glad to finally have this over with. I've been struggling with what I want to say in this video. I've already done one take before, but I didn't love it, and I prepared a little bit better. Just some notes on what I'm moving forward with. Typically, unlike the last video, I was playing on the easiest difficulty just because it makes it easier for me to just think about and explain what's going on. And typically, I'll be playing on the easiest difficulty for most of the puzzles throughout the game just because it makes it a little bit easier for me to explain what's going on while playing. But there are 4 difficulty levels. And in the remaster, the latest remaster called Zoombinis, there's both a story mode, a journey mode where you have to do 400 Zoombinis through the puzzles to Zoombiniville, and perhaps like most notably, as you get Zoombinis through perfectly through puzzles, they will increase through the 4 difficulty levels. Now, I did play through it on like story mode originally, but now I'm just going to go through the practice. Just play the puzzles on practice just because it makes it a little bit easier on me perfectly. Something interesting I want to talk about before I go any further is that the developers did a very interesting thing in truly making the game for all ages. Not so easy is probably go from things for like that would be good for 6 to 8-year-olds. Just like very simple puzzles that anyone can figure out. And then like once you get to the hardest level, very, very hard, you get to things that will be challenging to adults and even people with mathematical experience like I have. And I think that's fascinating. That was one of their stated goals in a document I read about Zoombinis. They wanted to make something that truly could appeal to everyone and could like result in mathematical thinking for the whole family, and just to increase mathematical talk across all the people in the family. Something else that's interesting is that each group of 3 puzzles I should say, focuses on different mathematical concepts. The first 3 that I did a video on the last time dealt with sets and logic, and that's what I talked about. Now, after that, the path splits into 2. You can take Zoombinis through the upper path or the lower path. I'm going to be taking the lower path through the deep dark forest today. And the deep dark forest, the puzzles there typically deal with functions and things called vectors, which I will go over in more detail. Something else I just want to say I admire about this game is that unlike so many other games that are edutainment based, and they mention this again in the document, it was just a very well written document about the developers and their goals. But they mentioned like the reward for playing through the game and solving math problems correctly is reward animations or snippets of gameplay that rely more on time pressure and are divorced from the educational content. They're divorced from the educational content, and furthermore, the edutainment games only really teach very specific patterns of thought, very specific algorithms, very specific problems. Addition, subtraction, multiplication, division, etc., etc. And that's something I really admire about Zoombinis, is that, and this is something they did really well, they integrated the play with the solving the puzzles. They truly integrated play with learning in an amazing way. And I just want to say, as an educator, it's very admirable how they've done that. Or as an aspiring educator, would be more proper. But enough of that. Let's get started with finding out about the fleens. Well, you're probably wondering what these green things are. These are fleens. Fleens are kind of like cousin creatures to the Zoombinis. And that can be observed through that they have similar variations in hair, eyes, nose horn, and feet. let's get started. The goal is to put Zoombinis right here, and then a corresponding fleen will jump down and chase them onto the tree branch over here. And the final goal is to get these 3 fleens, which are up on the branch above the the beehive, I'm sorry. But the 3 fleens are on the branch above the beehive to jump off so the bees get angry, chase the angry fleens away, and the Zoombinis can keep on moving to Zoombiniville. So, how do we do that? Well, I already showed you the basic mechanism for moving a Zoombini into the pit, and then how the fleen chases them off. Now, what does that have to do mathematically? Well, one way of thinking about it is functions. A function is basically a rule that assigns one object to exactly one other object. Like lines on a graph are functions because they assign some sort of x value to exactly one y value. Similarly, there's functions at play here. There's a function that assigns hair types for Zoombinis to hair types from fleens. There's functions for eye types of Zoombinis to eye types for fleens, and so on and so forth. For example, we see this Zoombini up here and the matching fleen down here. This Zoombini has a baseball cap, and this fleen has green spiky hair. So we know that whatever the function for the hair types are, the baseball cap is assigned to the green spiky hair. What's more, just a little bit of terminology, this is a special kind of function called a bijective function. And what that means is that on a graph, if every x is assigned to exactly one y, that is a function. If every y is assigned to exactly one x, then it's a bijective function. Essentially, if you know one, you know the other. The function has an inverse. If I know Zoombini has a baseball cap, then its corresponding fleen will have green spiky hair. If a fleen has green spiky hair, then I know that a Zoombini has a green baseball cap. And that's not true for all functions. One example would just be like a parabola on a coordinate plane where, for example, y equals x squared. If you say y equals 1, well, x could be 1 or it could be negative 1. That wouldn't be an bijective function because you can't work backwards. That said, let's take a little bit more look here. So, this is fascinating because the fleen right here does not match any of the characteristics whatsoever for the 3 fleens up here. None of these fleens have rocket feet, so none of the matching Zoombinis are going to have a propeller foot. None of them have a blue horn, so none of the matching Zoombinis will have red noses. They don't have 3 eyes, so the matching Zoombinis don't have sunglasses. And none of them have green spiky hair, so none of them have a baseball cap. Okay, so let's see. No propellers. I'm just going to sort these out a bit. No propellers. No sunglasses. No red noses. No baseball caps. And as you can see, we've already cut down the pool quite a bit. Let's throw this one out there. Oop. Well, well, well. So the ponytail matches pink spiky hair. So we know one of the Zoombinis with a ponytail will match this pink spiky hair fleen up here. What's more, pink sneakers correspond to these big wheels. None of these fleens have big wheels, so none of the matching Zoombinis will have pink sneakers. And that cuts down just a wee bit more. Let's see. None of the fleens have this fleen's eyes, So none of these fleens are going to match up with Zoombinis with dot eyes. Unfortunately, we don't have any more Zoombinis like that. But we have one Zoombini with a ponytail that still can match fleens. So this fleen right here will match with this ponytail, and we'll get one off the branch. Haha. Just a quick note, I'm going to just go over a little bit about like the other variations of this puzzle. Now, in harder difficulties, some of the characteristics might not correspond strictly, like a Zoombini's hair might correspond to fleen feet type instead of hair to hair, eye to eye, nose to nose, feet to feet. And that's just one way in which it becomes a little bit more challenging. I'm just going to offer an overview of what happens as the puzzles get a little bit harder with every puzzle I do. Just because I think that'll be... just so you're informed. I don't know why I do things, honestly. Well, let's keep going. Well, we know that this Zoombini, this fleen, doesn't have any of these eye types. And it does have a red horn, so it doesn't have a red, green, or yellow nose. Now, of the Zoombinis that can match the fleens on the branch, only one doesn't have a red, green, or yellow nose. This pink-nosed fellow. There we go. Okay. Now this last one has a pink horn, so the Zoombini has a green nose, and that narrows it down absolutely nothing. But here's something else. This fleen has a laser eye, and none of these four fleens have a laser eye. So, the Zoombini that matches this one won't have sunglasses, or dot eyes, or eyelashy eyes, or a cyclops eye, because those correspond to the four eye types that this fleen doesn't have. Okay. So we know that it's going to have eyeglasses, and it's going to have and the fleen has purple hair, so it can't have a baseball cap, or a ponytail, or a flat top. Well, only one Zoombini matches that description. And there we go. The fleens are going to get run off, and all the Zoombinis can continue on to Zoombiniville. But yeah, that's one way we can use functions. By working the function of Zoombinis forward, we can figure out what attributes can correspond to which attributes on the fleens, and using deductive reasoning, like I demonstrated, you can figure out which fleens match which Zoombinis and use them to get results. That's a lot of what mathematical thinking is. It's recognizing patterns and then using logic and reasoning in order to figure out what drives those patterns and how those patterns can be used to find other things. And that's something I mentioned this earlier, I know, but I just want to say I admire Zoombinis for discussing like how mathematics isn't just calculations, it's very much a manner of thinking, it's a way of approaching problems, but I'll talk about that more in my next video. Now for this one, this puzzle, Hotel Dementia, it's called, is terribly boring if I don't bump up the difficulty at least a little bit. On the lowest difficulty, it's just a sorting puzzle. You're sorting the Zoombinis based on a certain attribute, whether it's eye type, or hair type, or nose type, or foot type. You don't really know which, you have to figure out which. And there's a time limit. There's a time limit for higher levels too, so I'll have to do this quickly. But on the lowest level, it's boring, so I'm going to bump it up one, and that will lead to something mathematically interesting.
Nice, Charlie.
There's a squirrel band leader, but that's not terribly important. Hello everybody, it's me again. Sorry about that. Sometimes that puzzle in particular just takes me a little while to start thinking about it properly. which is ironic because it does tie into a class I took recently called linear algebra. But it just goes to show sometimes when things are unfamiliar, it can be a little bit challenging. Even when things are presented in unfamiliar ways, it can be a little bit challenging at times, and that's okay. Mistakes are only bad as long as you don't learn from them. So, what are the rules here? Well, you have to sort the Zoombinis into these hotel rooms before this clock runs out. You try and put a Zoombini in the wrong room, it will drop and you'll run out of a bit of time. Now, there's rules. Zoombinis can share rooms only if they share two specific features. We don't know what those are yet. Furthermore, these rows and columns are organized. Every Zoombini along a particular row of rooms will share a particular feature, and every Zoombini along a particular column of rooms will share a particular feature that's tied to a different attribute. Again, we don't know what is which. So that said, let's see, that one's right there. So let's try something totally different. Well, let's try this one. Oops. Okay. So this one has different hair, different eye, different nose, but same feet as this Zoombini. So we know that that either the row or the column is sorting based on feet. Because if neither the rows were based on feet, then there'd be no reason for this to not go right here. Oops. Well, it looks like the columns are going to be for different feet attributes. Now we just need to figure out what sorts the rows. Well, let's see. Oops. So this one has something in common with one of these two Zoombinis. Well, let's see. It doesn't share an eye, and it doesn't share feet. It does share hair with this Zoombini, but it can't be in this column because that organizes feet. Is it in this row? Yes. So, the rooms in this row all will have the same baseball cap hairstyle, and the columns of these rooms will all have the same feet. Wheelie feet. Let's get going. Once you figure out the rule, it's not too hard to sort them all out. You don't really need to put them in specific columns, just as long as you place them in a way so that each one shares a row with all the other Zoombinis of that hair type and shares a column with all the Zoombinis of that foot type, you're a-okay. I know this may be a little bit confusing, but I'll get to it. Oops. Forgot that that column was reserved for roller skates. Well, I'll rectify that. Let's see. Yep. And last but not least, and our Zoombinis are sorted.
Dream a little dream.
Thanks, musical squirrel. Anyways, so what did I just do? So, again, start out in the lower left-hand column. We know that the rows are going to be sorted by one attribute and the columns are going to be sorted by another attribute. We don't know which is which yet, and frankly, they're not assigned. It doesn't matter. We can just pop a Zoombini in the lower left corner, and it'll just accept it. Now, What happens next? Well, I take a Zoombini with exactly one attribute in common with it, and try to put it in a place where it has no attributes in common with the lower left corner. That way, I can see if that attribute is on the rows or columns or not. In this case, it wasn't. I tried to put the flat top with the propellers in the corner up and to the right, the lower left-hand corner, but it fell, so we knew that one of them was going to, that either a column or a row sorting was going to be sorted by feet. I tried it on the row first, didn't work out, so instead I popped it in a column. So then I knew that columns were for different types of feet. Then, how do I find the other one? Well, I take another Zoombini with one attribute in common with I'm trying to remember how I did it exactly. But the process is similar. Take a Zoombini with only certain attributes in common and try to put it in a place where it wouldn't be in common so you can see if it's accepted or not. In this case, it wasn't. I believe the second one I tried was had a baseball cap. And because the baseball cap couldn't very well fit in the propeller row because it didn't have the propeller column, I should say, because it didn't have propeller feet, I knew it would have to go somewhere in the same row. So that's when I realized rows were defined by hair types. And then once I knew that they were defined by that the columns were feet types and the rows were hair types, sorting out the rest wasn't the hardest endeavor in the world. You can just sort of build up from there. Again, the rows and columns for specific types aren't preordained. They're built up as you add Zoombinis to the grid. Now you might say that's neat and all, but what does that have to do with math? Well, first off, imagine a coordinate plane. Now, what's a vector? A vector is kind of like an arrow in a space. It could be an arrow in the 2D space of a coordinate plane, the 3-dimensional space that's all around us, 4-dimensional or 5-dimensional space, or really anything. And I'll get more into that a little bit later, like what dimension means, more or less anyways. But in a coordinate plane, you can think of a vector as basically just being an arrow from the origin to a point. Here's the thing about vectors. All vectors can be represented by two vectors, at least in 2D space, by combining the up vector, which is just like one unit up, and combining the right vector, which is just one unit to the right in like the positive x direction, if you're drawing a coordinate plane the normal way. Because no matter what point you are, no matter what point you're at on the coordinate plane, if you go a certain direction, forward or backward on the x-axis, and a certain amount forward or up or down on the y-axis, then you will be able to hit any point. And that's a very numerical way of thinking about vectors. And because that's a numerical example of what like vectors can be like. But a vector is more general than that. Really, a vector is kind of like a set, but in a specific order. A vector in 2D space might be a coordinate, like 3, 4. But Zoombinis can be treated as being like vectors too. Because a vector is basically like an ordered set. And a vector has one or more quantities in that set that define magnitudes in a direction. That's probably sounds strange again, but think about it this way. Like, remember the 0.34? That is a vector because it is a set of two quantities in a specific order x first, then y first. And that vector can be thought of as going 3 in the positive x direction and 4 in the positive y direction. Zoombinis can be thought of as vectors because they are a set of distinct attributes. Every Zoombini can have 5 hair types, 5 eye types, 5 nose types, and 5 feet types. So, in a way, Zoombinis are kind of like a vector with 4 elements, one for each attribute. And essentially what I did right here is I plotted each Zoombini on a coordinate plane. Except instead of the axes being x and y, the x-axis would represent different feet types, and the y-axis would represent different hair types, and the other two are just ignored. I just want to reiterate, if anything I'm saying doesn't make sense, feel free to leave a comment, or just, leave a comment. I don't really have any other way of contacting me available, I'm coming to realize. But yeah, just leave a comment. I'll try and clarify to the best that I can. But that's the takeaway from this, more or less. A vector, at least numerically, the way we think about it most often, is like an arrow in a space. But more generally, a vector is like a set, a set with like elements in a specific order, and those can be used to sort different things in different ways. And another important attribute of vectors is that the different quantities can vary independently of each other. Now, what does that mean? Well, that's what the next puzzle is for. Come on. Okay, there we go. I'm going to do this one on Not So Easy just because, Oh So Hard isn't bad. It just introduces a complication into what goes on that might make explaining the math a little bit harder. Okay, so what does this machine do? Well, it makes little mud balls and paints them a certain color, blue, red, yellow, pink, or green, and puts a certain hole in them. Square, triangle, star, circle, or diamond. And then when you press this little button right here, it flings it at a wall. Not exactly rocket science. Now what happens if I have the same color, but I change the hole shape? Okay, so when the color's the same, the ball will end up in the same row, but when the center hole is changed, it will end up in a different column. That's interesting. Well, what does that mean? We can think of the mud balls in their position on the wall as a vector. In this case, the rows, or the positions on the y-axis, up and down, would be the different colors. And the positions on the x-axis would be different holes in the ball. And once we figure out what colors go where, and what hole positions go where, we can send the balls to these bricks with holes in them. And when you hit a brick with holes in it, it sends that many Zoombinis up top, so they can continue their journey to Zoombiniville. Like if I hit this brick with 3 holes in it, then all 3 Zoombinis will fly up here, be catapulted more accurately. And something that this demonstrates really well is a vector's independence. The x value, or, any value of a vector can change without affecting any of the other values of the vector. I can change the color of a mud ball without changing. I can change the color of a mud ball and thus the row it will land in without ever affecting what column it will land in because the hole is the same. Similarly, I can change the hole and change what column the mud ball lands in, but never change the row because the color is the same. And that's what I meant earlier by independence. In vectors, you can change one attribute without changing another attribute, and that's something that's really important in a lot of things. I remember once I was tutoring someone in physics, and they're having a little bit of trouble with projectile motion in 2D space. Like, imagine throwing a ball through the air, and just like, imagine someone throwing a ball to another person on like a piece of paper. The ball couldn't move in and out towards or away from you, but it could move up and down and left and right. And they're having some trouble with the equations for that. Well, what we do, at least in like the basic physics class, is we treat it as two separate problems. The movement in the x direction is independent of the movement in the y direction. And we can treat that like a vector. If you throw a ball, because there's no forces acting on it in the x direction, its speed is going to remain constant. But in the y direction, because gravity is acting on the ball, its velocity is always going to be changing in the y direction. And you combine the two velocities together in the x and y direction, you get the total velocity vector. The velocity is traveling in both left and right and up and down. And that's just one very basic application of vectors. God only knows how many others there are. Oh, 2 Zoombinis up. I love the noises. Okay. Circle out. Okay, and this one will end up right in the 3 spot. Oops. I am an idiot. Anyways, this one will end up in the 3 spot. And all 3 fly to the top. But yeah. The different parts of a vector can change independently of each other. Just like how a Zoombini can have the same eye type, but you can change the hair to be different between 2 of them. You can change x and y positions of vectors, or lots of other things too. In fact, most character customization screens you can think of as representing vectors of a kind. Vectors of hair and eyes and noses and mouths and all sorts of other things. That's not a very mathematical use of it most of the time, unlike Zoombinis, but I still think it's interesting and fun. Let's try red. Nailed it! That was very lucky of me. Now, look. Because we know that the red ball will end up in this row, and because we know that a ball with a diamond hole in it will end up in this column, I know that a red ball with a diamond hole will end up right here where the 3 holes are. Nailed it. Vectors, this is just a very simple application of vectors, but vectors as a whole have so many applications in day-to-day life. The whole of computer science relies on linear algebra, which is a study of linear equations, which can often be represented as vectors. Lots of physics relies on vectors. Indeed, the back half of my quantum mechanics course I took this last semester basically dealt with treating quantum states, states of various particles, as vectors, or matrices. It's kind of amusing how so much of my college education basically amounts to a multi-year long linear algebra course, but I digress. Not that I mind terribly much. But vectors in linear algebra are used in optimizations, artificial intelligence, machine learning. They're used in programming three-dimensional graphics. They're used in transforming any sort of image, really. They are used in so much that's related to computers or productivity or so much in everyday life. And I just think that's really neat. I wish I could go into it in more detail, but this isn't really a time or a place. For one thing, it's kind of hard, I think, to express it in the depth that I would be able to while staring at a bunch of Zoombinis and without being able to draw or anything. But I might come back to linear algebra later. I'm not sure.
My, you've done exceptionally well.
Thank you, narrator man.
Carry on.
But yeah, that might be something I talk about a little bit more in the future. Just go over it in greater depth. But a little bit of review. A function is a rule that assigns items or attributes or elements of one set to elements of another set. And a function is bijective if every element of the second set is only assigned to one element in the first set. Basically, if you can go back and forth, if you can go from the first set and find out that there's only one item in the second set it corresponds to, that's a function. Now, if you can take an element in the second set and figure out exactly what element in the first set maps to it, then it has an inverse. You can go back and forth. If you know the one, you know the other. That's a bijective function. And that's a fancy word, and it deals with like some set theory stuff. But that's more or less what it means, just on a very basic level. A vector is like an ordered set of different elements. And those elements can be anything, and they can vary independently of each other. Like how changing the color changes the row the mud ball lands in, but doesn't change the column. Or how you can change the hair of a Zoombini without changing its eyes or nose. And vectors can apply in lots of different places and lots of different things. They're truly one of the most versatile items in all of mathematics. Something else I'd also like to mention, just briefly, is dimension. And while I can't get into it nearly in depth here, and it's a lot more complicated than I'm going to make it out, in fact, I do recommend you read Flatland. Flatland is an old book. It's like from the early 1900s, late 1800s maybe. And it was actually written by a mathematician, a mathematics teacher, who wanted to explain the concept of geometry and dimensions to some of his students. I think that's the story anyways. And the latter half of the book deals heavily with it and explains it better than I can. But dimension, roughly, is how many vectors it takes to create any vector in a space. How many different directions you can go in a space. For example, on this grid of mud balls right here, I can go up and down. Oh, I can't play the mud ball machine anymore. Nuts. Anyways. But with the mud ball machine, I can change the color, and so change the row that the mud ball lands in, and I can change the shapes, and I can change the column that it lands in. I can change where the mud ball lands in two different directions. Two perpendicular directions, two directions that don't interfere with each other. So, the mud ball machine has a dimension of 2. A dimension is basically just the number of different vectors that you can vary without interfering with each other and end up with every other vector in the set. And that's a strange way to think about it, but it's like, remember earlier how I said, just basically, you can get any vector in a 2D space by moving so many units left or right and so many units up or down? It's the same principle. It's how many axes you have, how many directions you have to go in order to make sure that you can get every point. Now what about like the Zoombinis? Well, the Zoombinis have different hair types, different eye types, different nose types, and different feet types. They would be a 4-dimensional vector, because the Zoombinis can change in 4 different directions. There are 4 different axes on which a Zoombini can lie. And that may be a little bit confusing. Again, if I'm not making myself clear, please leave a comment so I can try and explain myself a little bit better. That's all I have for now. Have a lovely day.